Okay, so today we're going to review some basic digital logic. Over today and Friday, we will cover the 7 basic gates that we learned in digital logic. First is the inverter. The state table for that. Pretty simple. If it's low going in, it's high coming out. If it's high coming in, low going out. One of the most simple logic circuits. It is often written as A prime or A bar as far as Boolean expressions are concerned. The AND gate the state table for that is like so. And it is in Boolean expressions represented by multiplication. So it's A star B or just AB. So pretty straightforward there. It is only high when both inputs are high, low otherwise. Pretty simple stuff. The OR gate is and state table for that is if either input or both inputs are high, then the output is high. In Boolean expressions, that would be written as A plus B. The XOR gate is similar to the OR, except it doesn't go high if both inputs are high. So it is only high when only one input is high. And that is in Boolean expressions represented by the plus with a circle around it. You will see that in the technical reference sheet for the processor that we use in this class. Next we're going to show the NAND. As the bubble on the output indicates, the output is inverted from the typical AND gate. So it is the opposite of an AND. The NOR gate is one when both inputs are low and low when any input is high. So that is the state table for that. Now these two are the universal gates. Which means you can form any logical function using just NAND gates or just NOR gates. The logic can be translated into that form sometimes easily, sometimes less obvious, but the any logic function can be generated using just NAND or NOR. Sometimes it's more efficient to use NAND and NOR gates because, pardon me, because NAND and NOR gates use fewer transistors than AND and OR on the internally. So if you can implement a circuit using NAND and NOR gates, you can use fewer transistors and less space on a chip. So, yes. Well, yeah, it's A and B with a bar over it, or A plus B with a bar over it. There is no dedicated symbol just for NAND and NOR gates. So, or you can do A star B bar. Yeah, or put parentheses around them like this. And with the apostrophe indicating that it's inverted. But this bubble here indicates that the output is inverted from what the symbol normally would be. So same state table as an AND gate, just inverted outputs. The last of the basic logic gates is the often overlooked XNOR gate. I include this because it has a really handy use. The outputs are high if the inputs match each other. So you can use this to check equality of signal, whether the signal is both high or both low. So it's a handy little gate that has its uses. The eighth gate that we're going to be needing to use is the tri-state buffer. And the state table for this is if the enable is high, it doesn't matter what X is, the out will be high Z. Did Manzoul cover this in digital logic? The tri-state buffer? No? I did in my section of digital logic. I didn't spend a whole lot of time on it, but basically the high impedance state is no connection. Say this is a battery. You have low, the high is positive, low is negative. The third state, the tri-stated state, is no connection at all, no charge. That's what high impedance state means. So if the enable is high, it's like there's no connection to either ground or power. If the enable is low, then whatever's on the input goes to the output. Okay? This is the exception to digital logic design principles where you can connect two outputs together. As long as one is in a high impedance state, you can connect, you will get a signal through from the other gate. I'll give you an example. So, say you have a select line Under normal circumstances, you would not connect two logic gates outputs together, because if one is high and the other is low, you create a short circuit, things start smoking, and we all know smoking is bad for you, so we don't want that. So the exception to that is when you're using devices with tri-stated outputs. So when S is high, this would be low, and this would be enabled. So the S, A, B, and out, you would have S is 0, 1, 1. Let's see here. 0 would be B, so that would be X. 0, 1, 0, 1. 0, 1, 0, 1. So what you have here is, if select is 0, the A buffer is in a high impedance state and therefore not connected to the output, but B's output is enabled, so when S is 0, B is shown on the output. When S is high, the tri-state buffer for A is active and B is inactive, so A is shown on the output, B is ignored. That is a multiplexer, a 2-input multiplexer using 3 simple gates. So when we get into buses, when you have multiple devices wanting to connect to the bus, you can't have multiple devices connected at the same time. They must have devices that are not that do not have access to the bus. Their outputs and inputs have to be in the high impedance state. So let's see here. What other? Let's see here. A little bit of a review on Boolean algebra. Properties that are the same as algebra. The commutative law. Property. The associative property. Same as algebra. Which basically means AB equals BA. And A plus B is plus C is equal to A plus B plus C, like so. Just like in regular algebra. Where things get a little weird is the distributive property. Now, A times B plus C is the same as algebra. But now A plus BC this is not like algebra. This is, but this one applies to Boolean algebra, just doesn't match up with what you learned in algebra in 6th or 7th grade. So manipulating of Boolean expressions can be done using those three properties. Now there's De Morgan's law. Where you have A, B prime equals A prime plus B prime. And A plus B prime equals A prime B prime. Written with the bars instead of the apostrophes, that's A, B, now one person has put it to me like this: break the bar, change the sign. So you're breaking the bar between the two variables and then changing the sign, changing the operator from an and to a plus, to an or. Break the bar, change the operation. Likewise with break the bar, change the operation. Works both ways. Let's see here. Some important things to remember. Some important properties to remember when dealing with digital logic. A and 0 equals 0. A and 1 equals A. A or 0 equals A. And A or 1 equals 1. We'll get into how this is handy knowledge to have when we get into the programming part of the semester, but keep these in mind. Now, another one to keep in mind, A XOR 0 equals A. A XOR 1 equals not A. So a exclusive OR gate can be used as a selective inverter. When one input is 1, it inverts the input, other input. If it's 0, it doesn't invert it. This can this has handy applications in a variety of instances that we will get into a little bit later. But let's see here. Let's see here. Well, I kind of went through that kind of quick. Is there any questions about digital logic review that you want me to go over again? A little bit more clarity, or is this all coming back to you from digital logic? Pretty clear? Okay. I just went over the basics. I didn't get into transistor counts or anything like that. But that being the case, we'll have a review quiz on Friday on number systems and digital logic. Yes. Sure, sure. Yeah, it's just the state tables for the various logics. Okay. What about the XNOR and the did you get the XNOR and the tri-state buffer? Okay. No problem. Have a good day, all.